So this is a lesson on designing a study. So remember, a study can be an experiment or an observational study. Sometimes we might just be gathering data, like doing some kind of survey. We can also do different kinds of experiments and observational studies. So today's objective is just to critically analyze published findings for appropriateness of study design implemented, sampling methods used, or the statistics applied. So step one in designing a study is to decide who is the study about. So you want to determine what population you want to study. Who is your population? Who is the entire group of individuals that you are interested in? And then determine from that, can I do a census? Can I talk to my entire population or get information from my entire population? Or do I need to do a sampling instead? And we talked about these two words last class. We talked about census being the entire population, and a sampling mean that I take some kind of sample from my population and talk to just that sample. So that's step one. Figure out who is your study about and decide whether you're going to do a census or if you need to do a sampling. Step two is to figure out what do you want to know about your population. What is my parameter of interest? Remember, parameter is the what do I want to know. It's the number or fact that is true about my entire population. So when we are looking at what we want to know about our population, we're going to formulate questions, whether that be survey questions or experimental or observational study type questions that will help you gather the data. One thing to be careful of when you are formulating those questions is realizing that questions or interviewers that influence the outcomes lead to what we call response bias. So if we are doing a survey and I'm asking a question, especially if that question is face-to-face, or even if it's on paper question that is very biased one way or the other, or is very leading one way or the other, that can influence responses, we call that response bias. So questions should be objective, and interviewers should be courteous and ethical and protect anonymity, meaning we want to make sure the students are, not the students, but the subjects are kind of anonymous if possible, so then they don't feel weird about answering one way or the other. And that's all to minimize bias, right? So this is an example of response bias. If I was doing a survey where I wanted to know, like, on average, what do my students rate me as a teacher on a scale of 1 to 5? But if the way I asked that question was said, hey, students, before I grade your tests, please complete this survey on my teacher performance. I would probably be, that survey is potentially a bit intimidating. You want me to grade you well, so you might be tempted to rate me higher than you truly think that I am as a teacher, so that I'll give you a good grade on your test. So that is an example of response bias. Step three is to figure out who to gather data from. So we know who our population is, and if we can do a census and actually talk to or get data from our entire population, then great. But if our population is really, really big and a census is too difficult or maybe too expensive, then of course we might do, or probably will do, a sampling instead. So we talked a lot about samples in section 1.2, all the different ways there are of taking a sample, specifically ways of taking a random sample. But we also had something called a convenient sample where we just kind of did it non-randomly and asked whoever was easiest to ask. So most times with any kind of study, whether it's an experiment or an observational study or just a survey, you will need to do sample from our population, and you'll have to determine how you're going to sample. Okay, so obviously we want to sample randomly as opposed to doing it with a convenient sample. But another thing that we need to think about is what we call the sample frame. Now we did kind of talk about this in our homework assignment from 1.2. This came up a little bit, but a sampling frame or sample frame is the pool of possible participants in the sample, right? So if my entire population is all of these animals, but I only sample from this group of animals and leave these ones out of the sample process completely, we call that undercoverage. Or an issue with our sample frame. So if there are individuals in the population who are not in the sampling frame or sample frame, this leads to what we call undercoverage, which can lead to bias. Right? We want to avoid bias in our studies as much as possible to make sure that our results that we get from our sample or from our survey are reliable and accurate and that they represent what we want them to represent. So how do we sample or how do we assign treatments in an experiment? So one thing is to be sure to use randomization, right? We randomly choose our subjects when possible. We randomly assign subjects to the different treatments in an experiment. We don't want to just let people choose or to choose ourselves without any kind of randomization. So if we let individuals either volunteer for the survey or volunteer or choose which treatment they have, this is not random, and it is likely that they will not be representative of our population, meaning that this group that volunteered to answer the survey question or volunteer to do whatever kind of experiment that they're doing, they're not going to represent the population very well. They usually are a very specific subset. So we call this voluntary response bias because people are volunteering. Usually if we're talking about a survey question, or if we think about like ratings on the internet of, like Yelp or whatever, usually people who are filling out surveys or rating things voluntarily are people who feel very strongly about that subject or about that place, and their survey results or their answers may not be really representative of what just like the average person in the population feels. Also consider timing of surveys to avoid bias due to non-response. So, for example, it would not be a good idea to do a survey on Senior Skip Day if my goal was to figure out how the entire population of McNeil feels about something. I wouldn't want to do a survey on Senior Skip Day because I wouldn't be getting any results from seniors. Even if I was trying to or randomly chose students, most of the seniors aren't going to be there. Or we don't want to use a method that is easily ignored. Usually phone surveys are a really bad idea because people don't really pick up their phones, especially for numbers that they don't recognize. So doing surveys via phone is not really a good idea anymore these days. Even email surveys can be not a great idea because it's easy to ignore them. So non-response bias is what we call it when maybe we pick a sample randomly, but not everybody who's picked responds. They can ignore it, or they're not there, or whatever. So that's non-response bias. Okay, so now let's look more specifically at experiments. So if I'm going to do an experiment to try to figure out an answer to a question between 2 or 3 treatments. So I have these treatments and I'm trying to figure out which treatment is better, right? Maybe I have 2 medicines and I want to know which medicine works better. I'm going to do some kind of experiment. So the following on this page is what we call a completely randomized experiment. So a completely randomized experiment means there's no grouping. We're just going to take our pool of subjects and randomly assign them to our treatments and then compare. So we have to start with our subjects, right? Whoever they are, whether they're randomly selected, sometimes they're volunteers, but we try to avoid that. But we have our subjects who are ready for our experiment. So our first step is to randomly assign them to 2 different groups. And those 2 different groups will have the 2 different treatments. So random assignment happens, like you see the little hat here. We could do that with a hat method, put the names of each subject on a little slip of paper, put it in a big hat, pick half of the slips out without replacement, meaning don't put them back, and then whichever half I picked out will be in group 1, the other half will be in group 2. I could also do this by numbering my subjects, so number them from 1 to 20, use a random number generator to choose 10 different numbers between 1 and 20, and the 10 subjects whose numbers were picked will be in group 1 and the rest will be in group 2. So some kind of randomization, we put them in the 2 different groups, then we impose whatever the treatments are. Usually we like to have a control group. A control group is a group that doesn't really get a treatment, or they might get that placebo treatment that we talked about last time, that the placebo doesn't really have any like actual impact on the response. So we can have a control group, especially if we only have like one treatment that we're really testing. So if like I just have one medicine and I want to know, does this medicine work better than just doing nothing? Then I might have a control group who gets either no treatment or they get like a placebo treatment. And then we're going to keep other variables the same for all groups. So if I'm testing a medication on like headaches, I want to know, does this headache medicine work? Well, I want to make sure that I'm keeping any other variables as constant as possible. So I might tell them, don't take other headache medicine while you're doing this. Maybe we might tell them to limit their outdoor activities so that they're not, getting like heat headaches, or we might just have certain things that we're keeping consistent and constant for all groups so we can make sure that we get good results. And then at the end, we're going to compare. We're going to compare the number of headaches they get, or their level of pain during a headache, or something like that, to help us determine which of our treatments did a better job. So that was a completely randomized experiment, but we could also have what we call a blocked experiment. So a blocked experiment is where we think there might be one group of subjects who will react or will respond differently to our treatments than the other groups. So we might want to separate our subjects into blocks because of obvious characteristics that may affect their response to the treatment. So maybe males and females respond differently to certain types of medication. Maybe different grade levels will have different abilities or understandings of our treatment. So we might want to separate our group of subjects before we even start randomly assigning treatments. So my first thing is I would have block 1 and block 2 separate. In block 1, I'm going to randomly assign my subjects in block 1 to the 2 different groups, give them the 2 different treatments, and then compare the results in that one block. And then in my second block, I'm going to randomly assign the 2 different groups to the 2 different treatments, and then I'm going to compare the results in that block. So block 1 might be all the males, and block 2 might be all the females. I'm going to randomly assign all my males to the 2 different treatments and compare that with the males. I'm going to randomly assign my females to the 2 different treatments and then randomly compare the results at the end. I like to think of a blocked experiment as really just splitting up my group into smaller groups and then really just running a completely randomized experiment within each block. And that will give us a better idea of like, how does this medicine work on males compared to work on females? Maybe the medicine does a really good job for males, whereas for females, maybe it doesn't do as good a job. And that's good information for us to know, right? Or maybe it works the same on both, but we wouldn't have really been able to tell if we had done a completely randomized experiment. If I do completely randomized, right, it's very possible that I could give most of the males this treatment up here and most of the females this treatment down here, and then it's really hard for me to tell whether that treatment actually worked better than this treatment or if it was just because of gender. The last thing I'm going to talk about in an experiment is something we call blinding. So blinding doesn't mean that we blindfold our subjects. Blinding has to do with preventing bias again. So when we do an experiment, the best experiments include some sort of blinding. Blinding prevents bias by hiding the treatment type from the observer or the subject or both. So blinding, for example, would mean if we have like a real headache medicine and then maybe a placebo, a fake headache medicine, like a sugar pill, we want those 2 pills or those 2 treatments to look and feel and act and whatever exactly the same so that the person who's taking them, the subject, doesn't know which treatment they have. They think they have no idea whether they have the real headache medicine or the fake one. Or if we're just testing 2 treatments against each other. We have 2 different treatments and we're going to see which one works better. If they look exactly the same, if they're both kind of the same size and shape and color, and the subjects have no idea which medicine they actually have, that is blinding. So if you blind one side, we call that single blind. When I say one side, I'm talking about the observers and the subject. So the observers would maybe be like the doctor or the nurse or somebody who's giving them the medicine. So it's also helpful if they don't know which treatment the subjects got. Because if the doctor knows this treatment got a fake pill or the subject got a fake pill and the subject says, oh, I'm feeling much better. And the doctor's like, no, you couldn't have been feeling better because you took a fake pill. That could sway the results. So blinding the observers, meaning the doctors or the nurses or whoever's giving them the treatment, is also helpful. So if we blind the observers as well as the subjects, we call that double blind. So if we're blinding both sides, we call that double blind. So the observers and the subjects don't know which subject is getting which treatment. And I always get the question with this when they're double blind. They're like, well, if they're double blind, then how do we know which medicine is which? somebody knows. There's somebody with like a clipboard that has a list of which subject is getting which treatment and is keeping track of all that. That's usually like the statistician or the person setting up the survey or the experiment. So somebody still knows and can do kind of that analysis and compare at the end. But anybody, the subjects themselves don't know, and then the observers would be anybody who comes into contact with the subject or is monitoring their progress. They also don't know which treatment that each subject got. They're completely blind to that. So that's what we mean by blinding, and it's just one more way that we can prevent bias, because if the treatment is indistinguishable, if the subjects don't know which one they have, then that takes away one thing that could potentially change their reaction or their response to the treatments. So that is it for experiments, and I will see you guys next time.